No. Okay, no, it's recorded. The coffee break, if there is to be one, will not be recorded. You should keep your video on if you can. It makes some kind of more lively feeling for the speaker. Also, please ask as many questions as you have. Since there is some kind of restriction, you cannot unmute yourself and so on due to the high number of participants. Please raise your hand if you want to speak. So for that, you go into the participants menu, and then there is a raise hand option with the small hand. You can click on that and I will be notified. In this way, I can just notice warn the speaker that you want to ask a question. And if there is any problem, any trouble or so, you can use the chat to send me messages. Unfortunately, you cannot chat with everybody for now. I will maybe give you this opportunity at the end of the talk. But during the talk, you can only talk with me, and please do that if there is any problem. So I will now, okay, Francesco already has his microphone on, so it's time for me to let Francesco speak, and I will give you about 45 minutes for that. Thank you, Francesco.
Okay, thank you very much, Charles, and thank you for the invitation. I would like to spend the first 10 minutes or something of this talk by giving you a kind of long introduction and an informal overview of the subject that we show you, so to be sure that everybody will be able to more or less follow also the more technical part of the talk. So one of the main achievements in programming language theory is the development of what we may call extensional analysis of programs. And these are just formal methods, let's say, aiming to answer questions such as, does the program terminate or does the program raise errors? And that more generally studies what program computes. And the main idea behind this analysis is that programs are black boxes. So we are not allowed to inspect program, but just to observe relations between the input and the output. And therefore we study programs for their input-output behavior. And this analysis has a solid mathematical foundation that builds in type theory, denotational semantics, and program equivalence, which is somehow let's say the main topic of this talk. There are also other kind of analyses that people studied in programming language theory. And in particular, the one that we are interested in today is what we may call intentional program analysis. And these are analyses differs from the extensional ones because now programs are white boxes. So we are allowed to inspect programs and we build analysis to understand how program compute. And you may have found this sort of analysis when, for instance, if you want to study program efficiency, security, or robustness variations. And in this talk, what we are interested in is the mathematical foundations of this analysis. Now, in order to make everything more concrete, let me show you two concrete examples of intentional program analysis that I will also use as running examples for this talk. So the first one comes from the field of information flow, and it is concerned with program security. So suppose you have a programs with two inputs, a public input and a secret input, and you want to understand whether the program is secure. So what do we mean by that? Well, let us suppose to have an external user or an external observer that can only observe the result of the program. And then we say that the program is secure if the external observer cannot infer any information on the secret input. So just by looking at the result of the program, it is not possible to infer any information on what was the secret input of the program, which means that classified information cannot flow out of programs. And just to have let's say, a trivial example, so suppose we have a program that takes a secret key as an input. It just tests whether the key is positive, and it tests whether the key is positive or negative. And obviously, this program cannot be secure because just by looking at the output of the program, we can tell whether, say, the key was negative. And as a second example, we consider program sensitivity. This comes from the field of differential privacy and program metrics. And here, what we want to study is robustness of programs with respect to errors or variations. So the scenario is as follows. So suppose you have one program with one input, and then you have a perturbation or a variation in the input of an epsilon, and we can think of epsilon as an error. Now we want to understand how much this error is amplified by the program and thus propagated until it reaches the output. And what people have developed to study these sort of behaviors is the notions of K robustness or K sensitivity, which means that whenever we have the error epsilon in the input, then the error in the output is at most K times epsilon. So K, the number K, now gives us somehow a measure, a law of how much errors in the input are amplified by the program. So now we have seen these two concrete examples, and there are at least, I would say, two questions that we should ask ourselves. The first one is, how do we guarantee programs to have these intentional properties? So how do we guarantee programs to be secure, or how do we guarantee functions to be K-robust? And the second question is, how do we reason about these sort of programs from an intentional perspective? So to answer the first questions, people usually consider specific type systems in which types now also gives information on these intentional properties. So for instance, we have a type that specifies that a piece of code is a secret or is a classified. And at the same time, you also have types that tells you that a function is K-robust or K-sensitive, if you like. Whereas concerning the second questions, of course, there are many possible answers that you may consider, such as, say, denotational semantics. But the answer that we wish to investigate in this talk is program equivalence. So just a quick reminder for those of you that maybe are not really familiar with these notions. So program equivalence, as the name suggests, it denotes a family of techniques, family of definitions that gives notion of equality between programs. And the idea is that programs are equal when they have the same operational behavior. And these notions of equality have been studied quite extensively, of course, because they are theoretically interesting, but also because they have many applications in fields such as program refactoring or optimization. And these are exactly the notions that allows you to, let's say, lift the standard arithmetic, the standard law of arithmetic inside a higher order setting, or that allows you to optimize programs according to some structural patterns. And there are many notions of program equivalence that you may find in the literature, but all the, let's say, the good one shares a common feature, namely they are compositional, which means that you can study the behavior of software systems by studying the behavior of their components in isolation, right? Okay, so that is the idea behind program equivalence. What we would like to understand is, first of all, can we use program equivalence for reasoning about intentional properties of programs? In fact, the standard theory of program equivalence is concerned with extensional properties of programs, which means essentially programs should be equivalent if they share the same extensional properties. So if a user is not able to detect any difference between programs from an extensional perspective. But here we are interested in intentional properties, such as security or robustness, and it is not clear at all whether the notion of program equivalence can play a role in this setting. But we can just look at the literature and continuing with our running examples, where we see that indeed program equivalence has been used and been developed to actually even formalize these intentional properties of programs. So for instance, if we look at the field of information flow and security, we find the notion of non-interference, which formalizes our previous idea that a program is secure. And we say that a program is secure if whenever we change the secret input, so key 1 here with another secret input, let's say key 2, an external user with public permission cannot detect any difference between the two programs obtained in this way. And similarly, we can use program equivalence to study program robustness, this time finding a notion of metric preservation, which states that a program is k-robust or k-sensitive if whenever we pass to the program two inputs, which are epsilon apart, so that differs for an error epsilon, then the resulting programs will be at most k times epsilon apart. So summing up, we have considered two concrete examples of intentional program analysis, namely security and sensitivity. And we have noticed that people reason about and study this property in languages with specific type systems where types now can give information on these properties. And we also seen that some specific notions of program equivalence have been introduced to model the intensional properties of interest and to reason about these sort of properties. And there are many other examples that you can find in the literature that I have not considered here, such as dead code analysis with the notion of proof irrelevance, but also strictness and resource analysis. And so now the questions that we should ask from a theoretical perspective is rather clear, namely, can we give a uniform account of all these phenomena? So we have seen two examples of intentional analysis of programs. We have said that there are many others, and what we would like to do is to develop a general theory of all these phenomena, exactly in the same way as we have general theory of a program equivalence and those of extensional program analysis. And concerning type system, this is something that people are studying quite a lot in these days, and there are many proposals. The one that I will follow in this talk, but I would talk more about that later, uses graded model types. So we have specific model types labeled with grades that essentially give us information, such as this piece of code is classified, this piece of code can be copied or erased, or this piece of code can be used k times, and so on and so forth. Whereas concerning uniform account of program equivalence, well, that's exactly the topic of this talk and what I would like to show you. But before that, let me remark that there are some crucial differences between the standard, the ordinary or extensional theory of program equivalence and its intensional counterpart. In fact, in the ordinary theory of program equivalence, programs are equivalent for any observer. So either they are equivalent or they aren't, and this must hold for any possible observer. When we move to intensional program equality, things are different because now the equivalence between programs actually depends on some observer's features, such as whether the observer has public or secret permissions. So for instance, suppose that an external user is checking whether two secret values are equivalent. Now, of course, the answer to this question should depend on the user permissions. So if the user has public permission, which means that the user is not allowed to inspect classified programs, then of course he or she should regard the program as equivalent, because she cannot just look at that at the programs, so she will not be able to detect any difference between these two. However, if the user has a secret permission, meaning that she can inspect these pieces of code, then of course what we would expect is the user to be able to discriminate between the two secret values. Okay, so that's more or less the setting that we want to study. And what I will show you in this talk more concretely, more precisely, is a theory of intensional program equivalence for languages with graded model types. The language we use actually is not that relevant, as our techniques actually can be easily adapted to other languages, but maybe I will tell you something more about that later. one of the main features of the theory that I'm going to present you is that now program equality is parameterized with respect to possible words, and these possible words actually act as the kind of the observer's features that we have seen in the previous example. And in that sense, we have intentionality as in logic. And also, this is also the reason why I use this terminology of extensionality versus intentionality. That comes from logic, and because here you shift from ordinary relation to relation over possible words, exactly as it happens in logic. And then I will also show you how we can understand, how we can view this this theory of intentional equivalence as the notions of program distance. That this way establish a bridge between two different approaches to program analysis. And the main results I will show you are some abstract compositionality theorem that can be instantiated to recover specific theorems such as non-interference or metric preservation, which are the one that we have seen in previous slides. All right, now before entering into technicalities, let me tell you something about related work, and I apologize for omission. So concerning the two running examples we have seen, program sensitivity and security, there is a rich literature on programming language techniques for this, and in particular concerning the program sensitivity. There is a line of research that dates back to bounded linear logic and to bounded linear types, which give rise to a family of intentional analysis for resource usage and complexity, for instance. Whereas metric preservation and information flow comes from the field of programming language approach for information flow. More recently, many systems have been proposed to somehow unify all these intentional phenomena, giving rise to theory of graded and quantitative types, and at the same time to the notion of a co-effect, which roughly can be defined as a family of program behaviors that try to analyze how code can be manipulated. And what I've called intentional properties can be also called co-effects. I don't know whether there is a kind of general terminology for this, but if you're familiar with co-effects, then you can just replace intentional with co-effectful, and everything works smoothly. And as I said, the kind of language and type systems that I consider in this talk are modal type system, graded modal type systems, in which we have modal types indexed by grades, and these grades indeed gives information on how code can be manipulated. And in the last years, there have been quite a lot of research on this type system. So we have, for instance, a new programming language called Granule, and we have also some nice work on the denotational semantics of these languages using graded monads and comonads. And in the last month, it has been also published a paper by Abel and Bernardi on logical relations, which is quite related to what I'm going to show you. All right, so let us now enter to the main part of the talk. So our goal, as I said, is to define program equivalence for languages with graded model types. And these languages has two main features. So first of all, they are linear by default, which means that data are resources. So we are not allowed to neither copy nor erase pieces of code. And we have modalities, graded modalities, that tells us how we can manipulate code. So for instance, we have modality that tell us that code can be copied and erased, or that can use k times, or that it cannot contain unclassified information, so that can use only certain scenarios, and so on and so forth. And unfortunately, graded model types are rather technical, but luckily for our purposes, we do not need to understand them completely, just a few aspects. And that's also one of the reasons why, as I said, our results are rather robust with respect to variations in the language, so they can be easily adapted, let's say, to languages with quantitative types. So what's the idea? Well, we start with some linear types, say recursive type, tensor types, whatever, it doesn't really matter. And we add modal S4 types. So we have these S4 modalities, which are actually indexed by grades, and grades come from a grade algebra, which is sometimes called a resource algebra or a capability algebra. You do not need to know what a grade algebra is. It's just kind of a pre-order semi-ring. It has a bunch of operations which are used to specify, for instance, how to compose pieces of code. Like, okay, here we have 2 pieces of code that can be used intuitionistically, and we use them into different parts of programs. So we want to join these 2, or we want to use them sequentially, and so on and so forth. But for the purpose of this talk, you can just consider a few examples, like algebra for resource usage. So now we have labels that tell us whether we can use programming in a affine fashion, in a relevant fashion, or an intuitionistic fashion. We have labels for security and labels for sensitivity. And that's all. So graded as for modalities. And of course, the language is extended with a constructor for boxing programs and unboxing programs. And the last piece you need to know is that when we want to type programs using these sort of type systems, what we have are the so-called graded judgments. So now we use judgment in which we do not only track the free variables used by a program, but we also label these variables with grades that tell us how the program used variables. So for instance, we may say that this program used variable x1 in an intuitionistic way, for instance. And that's all we need to know about graded model type. So let us move to program equivalence. Again, what we want to do is to identify programs with the same operational, but now also with the same intensional behavior. And operational behavior is actually straightforward. I mean, that's the standard operational semantics that you have in linear lambda calculi or in model lambda calculi, just a bunch of beta reductions. And it is worth noticing that these semantics actually do not mention anything about model types or about intentionality, which means that it is program equivalence that has to handle and to take care of intentionality. How do we do that? Well, as we have seen somehow in the introduction, one way in which we can do so is to move from ordinary extensional program equality, which is based on ordinary relation, to intensional program equality, which is now based on relation over possible words. And possible words represent, as you've seen, some user features, but you can also think about these words as information state or as resource system. And in fact, because after all, our calculus is substructural, we take as possible words monoidal preorders, and that's exactly what people do since the 70s when studies the semantics of substructural logic. And now one of the nice features of working with this relation over possible words, which I will call Kripke monoidal relations, but if you're aware of a better name, please let me know that, is that their algebra is pretty much the same of the one of ordinary relations. So exactly in the same way, we can study program equivalence by looking at the category and at the algebra of relations. We can now study intensional program equivalence by looking at the category of Kripke monoidal relations. And this category as object sets, and an arrow between a set X and a set Y is a map associating to each possible word a relations over X and Y in such a way that this mapping is monotone with respect to the order between possible words and the subset inclusion. Now, when in this category, we can define several notions of equivalence, such as logical relations. The notion of equivalence that I will discuss in this talk is applicative bisimilarity, because this is a co-inductive notion of equivalence, which is quite powerful, and that is something useful to have if we want to study intentional behaviors of programs. So applicative bisimilarity, roughly, is a notion as a set of equivalence introduced by Abramsky for the pure lambda calculus, and it is based on the idea that after all, lambda terms are just syntax for functions. And we do know how to compare functions because we have the function extensionality principle. So we may try to use the same principle to equate, let's say, lambda abstractions, which are just, as I said, syntax for function. We have obviously a problem of circularity, which can be easily overcame by using coinduction. So what we do is to define applicative bisimilarity coinductively as the largest relations between programs that respect the operational semantics and that equates lambda abstraction using function extensionality. And that's just applicative bisimilarity for, let's say, the pure lambda calculus. What we want to do now is to refine this notion, or to translate this notion in the setting of cryptic monoidal relations. And actually, that turns out to be straightforward for what concerns clauses on the operational behavior of programs, and for what concerns function extensionality, we just have to act locally in a possible word. So for instance, if we look at the clause here for function extensionality, that's just the same. The only difference is that it is applied in a given possible word W. The crucial part is to understand how to do that, how to equate programs of a given model type. And here, the idea is that model types somehow do not act on programs, but actually act on possible words. And what do I mean by that? Well, let us see an example. Again, we look at program sensitivity. And suppose we have two programs of type box k tau, and we want to determine if they are equivalent at word epsilon, where now epsilon is a real number. And here, the fact that the programs have type box k tau essentially means that these programs can be used k times. So what we want to say is that when the difference between these two programs, which are used k times, is epsilon. And to do so, well, we said, okay, what we need to know is that these two programs are delta apart when you use it just once, which means that they will be k times delta apart when you use it k times. And therefore, it is enough to require epsilon to be at least as big as k times delta. So that's the crucial difference. As you see here, we do not really act on programs. So, yeah, I mean, we unboxed them somehow, but that's not really relevant. What we do is to act on the possible word, which is completely different from the clause that we have here, for instance, for function extensionality, where the word is left unchanged, but we change the program. Here we more or less leave program unchanged, but we crucially change the possible word in which we are comparing programs. And the same story holds also for security. So and now the big question: how do we formalize and how do we generalize these ideas? And to answer this question, it is useful to take a slightly more structural perspective on program equivalence, which dates back to Reynolds, as far as I know. So we can think of program equivalence as assigning to each type a notion of equivalence between programs of that type. And now the crucial point in defining program equivalence is that, well, suppose we have a type and we build out of it a new type using some constructions F, then what we need to know, what we need to do in order to obtain program equivalence is to find a way to lift these constructions F to a new construction that now acts on relations between programs that makes this diagram commute. So what is the moral is that in order to define program equivalence, we need to find a way to extend construction on types or sets to relations. And these constructions have already been studied, first in topology and then in coalgebra, giving rise to the notion of relation lifting, which can be, or of a relator, also called the Lux extension, which can be straightforwardly generalized to cryptic monadal relation. This is just a mapping of relations that satisfy some of these properties. These are not really relevant. The relevant point is here what we have in the bottom part of the slide, namely that this mapping allows us to extend a functor on set to a Lux functor the category of creating monadal relations. So precisely realizes the extension that we need for program equivalence. All right, so what kind of construction do we need for model types? And it turns out that in order to model equivalence of model types, what we need are graded comonadic lax extension of the identity comonad. Let us decode this sentence. So graded comonadic, it just essentially captures the fact that we work with S4 modalities, which has a comonadic nature, which are graded. So we need graded comonads essentially. And the fact that we rely on the identity comonad precisely reflects our intuition that model types do not act on programs. They leave the program unchanged, they just change the possible worth somehow. And formally, this intuition gives us the notion of a graded comonadic lax extension, which again is a family of maps on quickly monadal relation, now indexed by grade. And although this is probably the main technical tool that we have introduced for this idea of program equivalence, its definition, again, it's not really relevant. What it is relevant to understand the whole story behind these equivalences is the bottom part of the slide, namely that when we have a graded comonadic lax extension, what we are doing, we are extending the identity comonad on set to a graded lax monadal comonad on the category of creative monadal relation. And now that we have this notion, we can complete our definition of a model applicative by similarity by saying that programs for the model types are related if they are related by the comonadic lax extension. And we have evidences that our notion of a graded comonadic lax extension is the right notion for this job, because their defining properties are exactly what we need to ensure applicative by similarity to be compositional, which now means that if we have two programs which are related at the word V, and it uses an argument according to grade J, then whenever we have two inputs that are equivalent to word W, but according to the comonadic lax extension of J, then we can pass this program as input, these input values to the program, obtaining, again, related program, but now at the word obtained by composing the word W and the word V. And it is a straightforward exercise to now instantiate this compositionality theorem with a specific grade algebra and possible worth, recovering metric preservation and non-interference results, which are just results that tell us that indeed all this business of graded model types indeed is indeed correct for guaranteeing the properties that we have in mind. All right, that's pretty much the story about for what concerns intentional equality. And I would like to spend the last 10 minutes of the talk by showing you how this business of intentional equality can actually be seen as a specific notions of program metric. And of course, given the time constraints, I will do that in a rather sketchy way. So one of the take-home messages of this talk is that if we want to model program equivalence, if we want to model notions of equivalence between programs, what we need to do is, well, first of all, to specify the suitable category of relations, right, in which we can, in which to model a program equality, and to introduce suitable notions of lifting of type constructions to these categories of relations. And if we are interested in extensional equivalence, we can just take the ordinary category of relations. If we are interested in intentional properties, that what I showed you is that one possibility is to take category of Kripke monadal relations. But there is, however, another sort of category of relations, which is the category of distances, which have been used, again, for performing now extensional analysis of effectful programs. And if we do sort of equivalence in this category, what you obtain is the notion of a program pseudometric. And it is actually quite easy to see that program distances are just some kind of notions of intensional equivalence, but it is enough to take as possible words now distances between programs. But what I also would like to show you is that even somehow the other direction holds, that namely that also intensional equivalence is a specific notions of program distance, which means that intensional reasoning and metric reasoning are pretty much the same. And one of the reasons to do so is that we have now a solid theory of program distance, which may help us to understand and to improve our intensional analysis of programs. And also because, as I said, program distance has been developed for studying, for performing effectful analysis of programs. And therefore, it gives us a way to combine effectful and co-effectful or intentional analysis of programs. So what is the story behind program distance? Well, it's actually quite simple. The idea is to refine relations into their quantitative counterparts, which means replacing the Boolean values with real numbers, sort of, and to refine equivalences into pseudometrics. And there is actually a nice environment in which we can study this process, which has been discovered or introduced by Lovier in his approach of to generalize metric spaces as enriched categories. And here we can say more concrete and work with the relations that take values in a quantile. Now, a quantile is just a complete lattice with a monoid structure on top of it. If you're not familiar with that, it doesn't matter. You can think to it as a set of abstract quantitatives, or we can just consider some examples. So indeed, we have quantiles. We have the Boolean quantiles, which allow us to recover ordinary equivalence relations. We have the Lovier and the strong Lovier quantiles, which are based on real numbers in a way. The first one using addition and the second one using binary maximum. And quantile relations over this quantile give us sort of pseudometrics for the Lovier quantile and ultra pseudometrics for the strong Lovier quantiles. We also have other more esoteric quantiles, such as the three-element change or the left continuous distribution quantiles, which is used for probabilistic metric spaces. And most importantly, we have that monotone predicates on possible words give us a quantile. So that now the distance between two programs using this quantile takes as input a possible word and returns whether the two programs are equivalent at that word. All right, so as I said, as we have a category of relations for extensional analysis, a category of cryptic monoidal relations for intensional analysis, we also have a category of quantile relations for metric analysis, for abstract metric analysis of programs. Objects are set, and arrows, as you might expect, are just quantile relations. And the identity relation is defined in the usual way, whereas we have a beautiful, well, at least in my opinion, definition of composition, which is given by this formula, which is oftentimes called the matrix multiplication formula, as it resembles the structure of the usual matrix multiplication. And we have this beautiful observation made by Lovier, which is at the heart of his analysis of metric spaces as generalized categories, that if we consider transitive quantile relations, where transitivity is defined using, of course, composition, and we instantiate them on the Lovier quantiles, that what we see is that transitivity gives us exactly triangle inequality. And of course, if you do that on the Boolean quantile, it gives standard transitivity. And additionally, if you instantiate transitivity on the strong Lovier quantile, you obtain the strong triangle inequality, which means that by taking equivalence quantile relation, we generalize both equivalence, pseudometric, and ultra pseudometric. All right, and as I said, now working with quantile relation or with quantile distances give us several advantages. And in particular, as I said, there is a rich literature on these notions, and in particular, there is an entire field of topology called monoidal topology, which builds over these notions. and I've used theories and results coming from that field during my PhD to define a notion of bisimilarity distance for programming languages with effects and type systems somehow resembling graded model types. And what we can do is to just take what I did and generalize it to arbitrary graded model type systems, obtaining a notion of bisimilarity distance, which is defined as you might now expect. So I don't give you details. You just replace the Boolean connectives, such as universal quantifications, with their quantile counterparts, which here, for instance, is given by the MIT. And on model types, what you use is, without much of a surprise, a comonadic Lax extension. I don't give you the definition. It's pretty much the same that we have seen before, but now on the category of quantum relations. I just show you one example, which is somehow a canonical one, which again has been noticed by Lovier. If we take the Lovier quantal also as a grade algebra, we have a comonadic Lax extension that just apply multiplication by a constant. And if we just observe that Lax commutative squares in the category of quantum relations generalize non-expansive maps, then by applying this comonadic Lax extension, what we see, what we obtain is a generalization of Lipschitz continuous maps. All right, and having this notion, what we also have is an abstract metric preservation theorem, which just states that programs indeed behave as Lipschitz continuous functions, where now Lipschitz continuity is understood according to using the comonadic Lax extension. And if we instantiate these results, taking the quantals of monotone predicates on possible words, well, what we see is that we recover compositionality. Now, some conclusions also on this part. We have seen intensional program equivalence for graded model types and compositionality theorems for modal applicative bisimilarity. And the same results can be proved for other notions of equivalence, such as Bohm tree-like equivalence. And that was essentially the first part of the talk. In the second part of the talk, I will give you a sketch of how we can regard intensional reasoning as a form of metric reasoning, and therefore intensional equality as a form of program distance, obtaining the metric counterparts of compositionality, which is this abstract metric preservation theorem. And now it is natural to ask, especially because I was very sketchy in the last part of the talk, what do we gain from abstract metric preservation? Okay, I mean, that can be aesthetically pleasant, but in the end, we have just reproved something that we already knew in a different setting. Now, what we gain from these results are combinations of effects and co-effects, or of intentional analysis and effectful analysis, if you like. And just in 10 seconds, how can you do that? Well, first of all, you add primitives for effects to your language, so that you can now, for instance, you have randomness, we have imperative stores, and so on and so forth, and we consider monads to interpreting these effects. Then what you do is to generalize by the bisimilarity distance, using now also what is called the monadic Lax extension. And I do not give you the definition, but again, this is the second take-home message of this talk. So first one, you need to find good categories of relations: ordinary relation, cryptimonoidal relations, quantum relations. Second take-home message, in this construction, you have to axiomatize and to find good notions of lifting, good notion to lift, to extend type constructors or set functor to this category of relations. For ordinary types, functorial extension, actually functorial Lax extensions are enough. For modal necessity types, for S4 modalities, because they are a comonadic nature, what we need are comonadic Lax extension. If we now add effects using monads, we have monadic effects and also monadic types, even graded if you like. So what you need are monadic Lax extension. That's the overall idea. And the additional condition you need is a Lax distributive law between the monadic and the comonadic lax extension, so that the intentional and effectful part of your language smoothly interacts. And once you have settled down all these ingredients, what you obtain is a new abstract metric preservation theorem, which now gives you compositional techniques for reasoning about intentional program behavior and effectful program behaviors at the same time. Okay, that's it. So thank you for the attention. And if you have any question, please do not hesitate to ask.
So thank you very much, Francesco. So before the questions, let us just upload Francesco. So I will unmute all of you. If I find again like that. Okay, so we can now thank Francesco. And it's now time for questions. So please raise your hand. So in the participants menu, if you have a question. So there is a question by Tom Hirschowitz.
Yes, thank you. Is there in this setting with effects and co-effects a correspondence between applicative bisimilarity and contextual equivalence?
Francesco, you need to activate your microphone.
Okay, can you hear me now?
Yes, yes.
Yes, I think so. No, there is no correspondence. I mean, the abstract metric preservation theorem gives us the soundness of applicative bisimilarity for contextual equivalence, but we do not have, let's say, the other inclusion. And you can see that already by looking at some specific effects, such as, let's say, non-determinism. So you don't even need to introduce co-effects to see that.
Okay, thank you.
There is a question by James Wood.
Hi. Yeah, I just want to put that one down. Yeah, I was going to ask, when you were talking about what was it? Comonadic lax extensions. Is what you've shown that so for example in Abel and Bernardi's crypto-monoidal relations, the modality can change sort of the relation-y bits of the relation as well as the world bit of the relation. Have you shown that just changing the worlds is enough?
No, I mean it can also change the relation. So that was that was just to give the idea that what these extensions do, it really do not actually act on program, but just acts on the way in which we relate them. And for instance, if you look at the example of security, here the comonadic lax extension actually changes the relation. So if, for instance, if we have if we apply the comonadic extension associated to the secret rate, and the relation is in the word public, then the comonadic lax extension just tells us that we have the trivial relation. Because if you don't have the rights to inspect classified programs, that you are forced to consider them as equivalent. So the comonadic lax extension can also change the relation. And you can actually also use them to move from finer and coarser relations, like say moving from, I don't know, applicative bisimilarity to alpha equivalence, because now your extension might say, okay, now you really have to look at programs syntactically, or the other way around.
Okay, yeah, because I have wondered about whether just changing the worlds is enough and you could sort of encode everything in the world, but I don't know whether that's
well,
something that would be interesting. Or...
I mean, most of the times you can define. I do not have this in the slides because it's rather technical. But most of the times, I mean, in all the examples I'm aware of, you can define comonadic lax extensions by giving a sort of action between the grade algebra and possible words. So you just need to give a function from the grade algebra times possible words to possible words that has to satisfy some structural properties. And in that sense, you have a large family of comonadic lax extension that simply changes the word. But I don't know whether these are in general enough.
Okay, thanks for the answer.
Thank you. We now have a question by Gordon Plotkin.
Hi, Francesco. Thanks for a great talk. Lots of interesting structure. Thank you. So how about denotational semantics? You have worlds, so you could do some kind of pre-sheaf semantics over the worlds?
I think so, but I have not yet really looked into that. What you can do for sure, what I know is that building on this category of cryptic monadal relations, you can consider the categories that as objects, sets and relations, in particular relations which are, let's say, reflexive and transitive, and as arrows you consider a commutative square. And that might have the shape of a sort of pre-sheaf categories. I don't know whether one can find a general model based on that. The only works I'm aware of on denotational semantics actually just consider arbitrary categories and monads and comonads on that.
Yeah, Abadi had some kind of denotational semantics for his security thing in that particular case.
Yes, but that's a very different framework somehow, because also Abadi uses monads to model program security. Whereas here we use model types and we have a comonadic treatment. But indeed, for some examples, the comonadic relation, the pre-sheaf semantics works fine. And here we have what we can extract from this is a relational denotational semantics, and I don't know whether from that one can also extract a more general pre-sheaf semantics that works fine for any possible, for arbitrary graded model types.
Okay, can I have a second question? Is that allowed?
Of course.
So you began to hint at the end about monads and algebraic operations. So
yes.
It would be interesting, and maybe you've already thought about it, to have the things fit together, like the algebraic equations could be different at different worlds.
Yes, because I think so. Yes, yeah. I think so. Although this is something I have not yet looked into that, but there is for sure a world story that could be investigated, or equations at possible worlds. And for instance, this has been done in concrete cases, such as you did for quantitative algebraic theories, in which you have equations that all are possible words, which are real numbers, that gives the distance between the terms. And I think one can do that for general possible words. But I don't know. I have not yet looked into equations for algebraic effects and possible words. I mean, I just investigate that from the, let's say, the more abstract perspective of relation lifting, and not from, let's say, the equational perspective.
Okay, thanks very much.
Thanks to you.
Thank you very much. Are there other questions? If not, I think we can thank Francesco again. So just the same, we can clap.
Thank you very much. Thank you.
So, thank you all. I will now stop the recording